A problem can be solved in different ways with different algorithms. Clearly, we want to use time and memory efficiently. So naturally, the different algorithms that exist that solve the same problem, obviously the different versions exist because someone obviously tried to create an algorithm to solve the same problem by making it more efficient in terms of both time and memory. And the only way that they can represent if an algorithm is more efficient is by a standardized method such as the big notation. And it is a very good method to represent whether an algorithm is more efficient in terms of time and space. A way of comparing the efficiency of algorithms has been devised using the order of growth as a function. Now, the reason it's called order of growth is because when I increase the size of data for a particular algorithm, the running time or the space requirement for a particular algorithm may increase. Now, by what factor does it increase? Does it become exponentially increased? Does it increase by 2? Or doesn't it increase at all? I mean, it's quite possible that it doesn't increase at all, no matter how big of a size you give it, it may not increase. The complexity of space requirement may not increase at all. So this is what the big O notation is basically representing. Big O notation is used to classify algorithms according to how the running time, which is known as space requirements, grows as the input size grows. The letter O is used because the growth rate of a function is referred to as the order of function. So that's what the O notation represents, the order of function. And obviously for representing these limitations or maximum values, we will be considering the worst case scenario in any particular algorithm. So if, for example, I'm performing linear search, so there's a mention about linear search over here. So if I'm talking about linear search, so what's the worst case scenario for linear search algorithm is that the element I'm looking for is at the end of the array somewhere. So that means for linear search, I will have to access all index positions to reach that desired index position that I'm looking at. So this is the worst case scenario. So to calculate the actual limits, the maximum time and space requirements of any algorithm, we will be considering the worst case scenario. Considering linear search algorithm, which we discovered in paper 2, chapter 13, the worst case scenario is that the item searched is the last item in the list. Best case scenario is obviously it's the first item. Baki, its average case is somewhere in between. But the worst case is that it's at the very end. The longer the list, the more comparisons have to be. If the list is twice as long, twice as many comparisons have to be made. Generally, we can say the order of growth is linear. In this case, that if I increase my array size from 10 to 12, if it was 10, I would have to do, worst case scenario means that I have to access 10 index positions. So if I increase my size of array to say 14, it means that I will have to access 14 different index positions. So as you can see here, my increase of size of elements in my array is linearly proportionally. So it's increasing linearly with respect to the time it requires to find that element. So if I have 15 array elements, I will have to compare 15 different index positions to access my worst case scenario, which is the last element in the array. So if I increase it to say 50, I will do 50 requirements. So my order function is growing. My cost, my time and space complexity is linearly increased, not exponential. It's not that I increased one element and the cost went up 10 times. No, if I increased one element, my cost went increased by one element. So it's a linear growth. We write this as ON, where N is the size of red. So there is no exponential, this is linear growth. Now let's consider the bubble sort algorithm. As you remember, this is, for example, the bubble sort. In fact, not only is this bubble sort, this is the inefficient bubble sort. Now by inefficient bubble sort, you can see the inner loop is actually a counter control loop, which means that if I have, for example, N elements, this will require N minus passes at all costs. So this is the inefficient bubble sort approach. Now, that's why, and this is also the worst case scenario. So if, for example, this also represents the worst scenario. If you remember, that we discussed this when we were talking about bubble sort, that the worst case scenario in bubble sort is that if I have n elements, I'll have to do at most n minus 1 passes. Now, it doesn't matter that if I'm using for loop in my inner loop or while loop, counter conditional loop, because in any case, I will have to reach the worst case scenario, because for order of O, the order of growth notation, I have to keep in mind the worst case scenario. And for bubble sort, the worst case scenario is that for n elements, I have to do n minus 1 passes. So it does not matter that I'm using the inner loop as counter controlled or while loop, because I will be using the worst case scenario at all cost. The reason that we use the while loop as the inner loop is because not every scenario is the worst case scenario. And it's quite possible that I am done sorting all elements within the first or second pass. In which case, if I am using this algorithm, even if my array has become sorted in the first and second pass, I will still require to do n minus 1 passes and I'm not basically doing any sort of swapping in any of the other passes, and my array has already been completely sorted by the second pass. But since our concern here is the worst case scenario, that's why we will use this algorithm, which tackles the worst case scenario in every array, regardless of whether it requires all n minus 1 passes or not. The worst case scenario is that you will require n minus 1 passes. So based on this, let's look at this table. If let's say I have one element in my array, I have to do no comparisons. It's already sorted. There's no comparison required. Now, if you remember that if I have the way bubble sort works is that I take two elements in my array, I compare them with each other, and if they are out of order, I swap them. So at 2, I'm taking two elements at a time and swapping them. Now, for two elements, I only have to do one comparison and I'm done. And that's it. If those two elements are in order, I won't swap. And if they're not in order, I will swap and my 2-element array is finished. However, if I have 3 elements, that means I will have to do two elements, 2 comparisons in my first pass, and then finally my 1 comparison in the last pass. Now, if you remember, for 3 elements in the first pass, what am I doing is I'm comparing element 1 with 2. And then if swapping is required, I'll swap. If not, I'll do nothing. And then in the second comparison, I'm doing 2 and 3. And this is how my first pass is done. Now, if you remember in bubble sort, after a pass is completed, my last element is assumed to have reached its destined position. In which case, in the next pass, I will not be considering this last element as part of my array because it's already sorted. So that's why in the next element, I have n minus 1 elements to compare. So in this case, in my next pass, I only have 2 elements to compare. And for 2 elements, I only need 1 comparison. So in the first pass, I need 2 comparisons. In my second pass, I only need 1 comparison. So if I have a total of n elements, I have to do a total of 1 plus 2 comparisons. Similarly, 3 elements, I have to do 1 plus 2 comparisons. On the other hand, if I have 4, in the first pass, I will do 3 comparisons. That is 1 with 2, 2 with 3, and 3 with 4. Assuming that 4th element has reached its destined position, in the next pass, I will do only 2 comparisons with 3 elements, 1 with 2, 2 with 3. And in the final pass, with 2 elements, I'll be only required to do 1 comparison. So this is what happens when I have a size of n, 4. That means I need a total of 6 passes. So 6 comparisons. For 5 elements, I need a total of 10 comparisons. First pass, 4 comparison. Next pass, 3, then 2, then 1. And for 6 elements, I require 15 comparisons. First pass requires 5. Next pass requires 4, then 3, then 2, then 1. Now, basically considering this trend, we can consider this formula. What? Half multiplied by n multiplied by n minus 1, which basically means what? Half into n squared minus n, to basically represent the value of number of passes. Check this out. Does this formula really apply here? If I have, say, two elements, n is 2, this is 4 minus 2, which is what? 2 divided by 2, 1. So for two elements, I need one comparison. So this formula works. It's okay. And it hopefully will work for all other elements. So basically considering this pattern, I can say that this formula for calculating the number of passes based on the total size of the array, this formula should work just fine. For every large n, we can disregard all factors except the largest we get in n squared. So the order of growth is actually just n squared. So now if you consider the fact that if I have an n square here, now this line is very important. Let's just say that if my size of array increased to 100 elements. So basically the 100 elements, when I take a square of that, becomes 10,000, I think. Yes, 10,000. 10,000. Now 100 elements, that means a 10,000 value. Now if I subtract 100 from 10,000, it's only 9,900, which is not a significant difference. So basically this n square is the real thing that causes my number of comparisons to increase drastically. So even if I have, say, a bigger number, let's just say if I have a big number, say 1,000 elements. Now because of 1,000 elements, my comparisons will reach up to 1,000,000. Now, even if I do subtract 1,000 from 1,000,000, that's not a significant difference from 1,000. So basically the real thing that I am considering here is this number here, because this is the number that really makes a difference. And if I have large value of n, this n square will cause a huge number of comparisons. And this subtraction of n really doesn't have that much effect on it because it's just n. Whereas this n square, because of the square itself, it causes a huge change of comparisons. So for the sake of representing the O, the big O notation, my n square should give us a fair idea of the time or space complexity of a bubble sort. As you can see here, the order of growth for both bubble sort and insertion sort is represented as n squared. And the minus n is insignificant. It doesn't make that much of a difference. So just for the sake of representation, this minus n is not included because the real factor in increasing size is this part, n squared. So if I have large value of n, this n squared will cause the number of comparisons, which is the real thing that takes up processing time as well as space. This is the real thing. And because of this comparisons, the number of comparisons, because of this n squared, the number of comparisons increases very, drastically based on the size of this array. Similarly, if we consider the binary search algorithm, now this is binary search. So binary search algorithm, as we discussed in the previous lectures, with each iteration, this algorithm halves the number of values in the data set. So if I have a total of n elements, in the next pass or the next iteration, I will have n minus 2 elements. So if you remember what binary search does is basically reaches the midpoint. If I'm looking for a particular element and this is an ordered array, I will first reach the mid of the array. If the element I'm looking for is greater than the element at the mid, so that means I have to focus on the right side of the array and the left side is ignored altogether. Thereby, at every iteration, my array size is reduced by half, and thereby reducing my searching effort. That's the beauty of binary search. Now, basically, if you look at this, with each iteration, this algorithm halves and the number of values in the data sets. So my size in each iteration is becoming half. So if I have n, at each iteration, it becomes half of n. This iterative halving of data sets produces a growth curve that peaks at the beginning and slowly flattens out as the size of the data sets increase. This type algorithm is described as O log base 2n. So basically what happens is that at a certain point, the complexity increases. And after that, there is no further increase and the complexity stays stable. So no matter how large the data set becomes, it's no longer increasing. It does not increase beyond a certain point. As we can see here with bubble sort, if I have the number of elements increasing, the size of my comparison is increasing by the square of those elements. So it's basically the size of elements causes my complexity to be squared every time. So it creates a very large value. On the other hand, in binary search, the size of the array increases and the complexity of my search algorithm also increases. But at a certain level, the complexity sort of flattens out and there is no longer any further increase in the complexity. So this is known as a O log base 2n is notation for binary search. As you can see here, let's just say if I have an order of growth for a this element, and simply what I'm doing is that I'm accessing an array list and I'm accessing the first element. So the order of growth is 1 here. So basically the complexity algorithm does not change regardless of data size. So I'm simply accessing one index position. No matter how big the array is, it doesn't matter. I'm simply accessing the first index position. So there is no change in the algorithm. There's no change in the complexity. No matter how big the array becomes, because I'm just concerned with the first index position only. So there's no change in complexity whatsoever. Similarly, if I'm performing linear search, as mentioned before, linear search is ON. Now, ON means your linear growth. So if I have n elements, my comparisons requires, I will require n comparisons. If I have say 5 elements, I require 5 comparisons. If I have 6 elements, I require 6 comparisons. Because again, I repeat, we're considering the worst case scenario. And the worst case scenario is that maybe the element is stored at the end somewhere. So this is linear growth. Size of array increases and my comparisons also increases by the same factor. There's no exponential in growth, exact same rate. So this is linear growth. So if you would plot the growth, the time requirement versus the size of the array for the linear search, it would be a diagonal line. It would be a standard diagonal line showing a linear growth pattern. Similarly, for binary search, the total time increases as the data size increases, but each comparison halves the data set. So the time taken increases by smaller amounts and approaches a constant time. So at some point, the time required for the size of the array stops increasing and it becomes a standard time. So it's not mentioned here what that size of the array can be, but it's predicted, it's seen that this order of growth function applies for binary. So it's been observed that larger the binary search data sets increase, the complexity and the time taken, the time and space complexity increases at a certain level, and at some point with certain size of an array, it stops further increasing. Before that, it started increasing by smaller amounts only, and that at one point with a certain size of data, it stops any further increasing and it becomes a constant time. So this is represented by O log base 2 of n. Finally, this is known as polynomial growth. So basically, if I'm performing, say, an n bubble sort on, say, n elements, the comparisons that I will be performing will be n squared. So basically, it will have the size of my array, size of my data set will have a very polynomial growth or exponential growth on my space and time complexity. So the larger set will cause more comparisons, thereby more space and time complexity. Polynomial growth is common with algorithms that involve nested iterations over the data set. As you can see here, we are using a nested loop here. So if each outer loop, my inner loop for each outer loop, which is controlling the passes, for inner loop, I'm doing all comparisons in my own complete array. So basically, this is a nested loop structure. So for nested iterations, your complexity usually reaches for O n squared. Finally, this is O n power 3. This is also polynomial. It's deeper. So if I have 3 layers of nested iterations, for deeper nested iterations, and even further deeper nested iterations, my complexity for the overall algorithm, both space and time, also increases by the number of nested algorithms I have. So if I have 4, for example, nested loops, then in that case, my complexity will increase by n by 4. So that means even a slight change in my data set will cause my space and time complexity to increase. If I have four loops, nested loop, for example, for my space and time complexity to be increased by power of 4. So that's a very huge polynomial growth. Finally, this is a recursive function. So for example, this is known as 2 power n. This is known as exponential growth. So basically, if my data size is n, and if I, for example, I'm using a recursive function, the complexity of such a function will increase by the order of 2 powers. So again, this also results in huge gains. Now imagine that if I have, say, 32 numbers, 32 numbers in my data set. So 32 numbers in my data set will cause this function to increase by 2 power 32, which is 4 billion, roughly 4 billion comparisons. So that's a huge growth. Now this is huge, huge. So every nth element being added increases the 2 power, and this causes an exponential. So if I'm increasing by the n power, so n power 1, n power 2, n power 3, so on and so forth, that's polynomial growth. And n power 1, which is actually just n, that is linear growth. N power 2, 3, this is polynomial growth. And this is used for nested ifs. N is used for linear growth. Log 2 of n means that there is a growth till a certain point, and after that, the cost and time complexity stops increasing any further. And finally, if we have 2 power n, this is known as exponential growth, and this causes my space and time complexity to increase on the factor of 2 power onwards based on the size. Now, space complexity refers to the amount of memory required, as mentioned before, for a growing number of values in the data set. And time complexity obviously requires the overall time required, clock cycles or whatsoever, to solve a particular algorithm using a particular data set. So this is basically this is the use of bigO notation, and these are the different order of growth values for different algorithms were decided based on the data sets of each.